Recording is rolling. Today is Thursday, October 6th. So you guys know that tomorrow is the last day of quarter one. So check focus for all your classes. Make sure that all your assignments are in. You're not missing anything. Because tomorrow is a hard deadline. Like if you turn anything next week, then it's just not going to go in the system because there's no school Monday. And then yeah, so tomorrow's like it. All right, so from you guys, here's the last two assignments that are going in for quarter one. There's the chapter 4, chapter 5 puzzles. Now, I gave you guys this page a long time ago. I've given out all the extra copies, well, except for this one, just using it for the video. So if you still have this page from a few weeks ago, then you have to print it out from Google Classroom. You guys know all the documents are in Google Classroom, right? And then the other assignment that you have to turn in by tomorrow is the Forces quiz. You guys have had that a few days. Some of you guys have already turned that in. If you already turned it in, then it's going to be in the system. If you haven't turned it in yet, then that has to come in tomorrow. If it doesn't come in tomorrow, it just has to go in as a 0, and then that's going to get locked into your grade. Okay? All right. All right. Any questions about school stuff in general? Okay. Oh. All right. So you guys going to bring me this Forces quiz tomorrow if you haven't read it yet, right? Okay. All right. Let's switch over and finish this lab. It's a Centripetal force lab. So you guys remember yesterday you had PVC pipe, a string, a couple of Play-Doh canisters, and you were wheeling this around. And you could set up like a balanced situation where if you got this top canister going at just the right speed, right? Notice I'm not saying velocity because the velocity is changing all the time because the direction is changing, but the speed might be the constant. That's the magnitude of velocity, right? So if you get going just right speed for knowing what this mass is, what this weight is, and what the radius of the circle is, right? Circle size. There's so many to balance all those variables. And I can call the tension in the string the centripetal force that's holding this spinning mass in balance, right? Circle with equal size. And that tension is equal to the weight of the hanging canister. Right, so you guys got a bunch of data yesterday. Remember, the way you approach this is I split you guys up into 3 different groups. Right? And some of you guys tested these 2 variables against each other, controlling for these 2. Some of you guys were in a group that tested these 2 variables against each other, controlling for these 2. And some of you guys left the canisters alone altogether. Once you closed those, they were just sealed. And you made different size circles and said, well, what's the resulting speed, right? So each of you has a third of the story. We're going to take those 3 stories. We're going to come up with one master equation that's going to link these 4 variables together. They're all going to fit into one equation. Okay. All right, you guys ready to go? All right, so I'm going to switch my screen over. Say present screen. Let me bump that. Okay, get rid of these. Yeah, get rid of that. Get rid of that. Whatever. Okay. Present screen 2. Share. All right, pull up a page for you guys. All right, and I'm gonna need some data from you guys. And so first group is the one that was changing out the weight of the hanging canister. And so who was in one of those groups? That would be where the hash marks are all kind of in the center of the page. Who was changing out the weight of the hanging Play-Doh canister yesterday? All right, so I'm gonna take a trip around the room and see if I see a paper that looks anything like that. All right. Actually, I think this one will do it. All right, so I'm gonna steal this data right here. Okay. Oh, let's do some quick hypothesizing before I start plugging numbers in, and this is gonna automatically make the graph for us. Okay, so guys, for a heavier canister, suppose you make that hanging weight heavier. How do you think you'd have to spin the top weight? Faster or slower? Faster, right? Faster. So do you think this is going to kind of trend upish? Right? Yeah. Now, how exactly upish? It's going to be a direct relationship. It's going to, but we're about to find out. So we got 3,000 millinewtons. We got 1,000 millinewtons. We got 200. Popping all these numbers all the way down. Okay, there's another 1,000. Looks like 150. All right. Oops, sorry, that's 500. All right, so this is the weights. What's the corresponding speeds here? So we got All right, so thank you. All right, let's see what we're gonna do with this. Tell you what. Here's what we do. I'm gonna pull up an ideal solution for this one, because this one of those labs that if you're really careful and meticulous with like the procedures and exactly how to do this, that you keep your circle the same size, you're really good with the stopwatch, you're like not grabbing the plated buckets and stuff, and the graphs should come out pretty good. And if not, they should be kind of scattered. But here's like an ideal answer. Right, so I've got pre-rigged up. Okay, so do you guys see on the front of your lab page, see the top left graph says V versus weight hanging? Do you guys see that? The top left graph says V versus weight hanging. That's that graph right there. Now this one says V versus F, but you guys know F stands for force, and weight is a type of force. In fact, the weight is providing the centripetal force ultimately because it's the same as the tension. Okay, will that be true? All right. So everybody's making the first graph, unless you already made it if you're in one of these groups, right? So the top left graph, you guys remember how graphs work, right? The title tells you which variable goes on which axis. According to that title, V versus F, which variable is on the vertical axis? V. Yeah, it's always like Y versus X, right? Yeah, so you got, go ahead and label your vertical axis V. That stands for speed today, right? And that's in meters per second. Okay. Scale it, looks like 0 through 8 about. Okay. And then on the horizontal axis, label that one F for force. Okay. Now, of course, that's the weight of the hanging bucket. That's also the tension of the string, which provides the centripetal force that was holding the top bucket in place. Say, like in a circle of constant radius. Okay. And the force is in millinewtons. So you labeled force in millinewtons. Okay. Went ahead and scaled it. Okay. Now, you could get a graph that looks pretty much exactly like this for some given radial size and mass of the top canister. Okay. It would work out just like that. And there you go. Actually, probably different combinations of those things could get you all this graph. Okay. But what we're interested in, since we're trying to piece a formula together, we're saying, well, what is the relationship between those two variables? Now, how'd you guys hypothesize ahead of time? You said, well, it should kind of trend upward-ish, and that's definitely the case, right? So for larger weights, it has to be greater speeds. But that does not look like a direct relationship, right? It's not a straight line, right? Like if you triple the weight, it's not going to correspond to a tripling in the speed, right? What do you guys think that curve looks like? What basic shape? Anybody have a guess? How many guys think it looks kind of like a sideways parabola? Sideways parabola, right? Is that same thing as a square root? Like a square root, right? Right. So I'm going to suspect that is a square root relationship. Now, how can I know for sure that's a square root and not, say, a cube root or a fourth root or some other kind of root, or maybe just some other kind of graph that looks kind of like a root, right? And the way I can confirm that and actually get more specific, more specifically the relationship between those two variables is say like how curvy is it exactly, is to linearize that data. It's okay if I switch the screen. You guys got that graph? Okay, so let me switch over here. And now what I'm about to do is a trick that we've done before in this class. Right? You guys remember the very first week of school, I had you guys graph properties of circles like area versus radius, came out to a parabola. Then I had you guys graph area versus radius squared, and that linearized. In fact, the slope of the linear graph was pi, because area equals pi r squared. Right? We're going to do something pretty similar to that. So what it looks like right now is that the speed is proportional to the square root of the force. I meant to draw that graph again, but that's just the graph that you guys just did, right? Right. I suspect that this is the case. See that little squiggly symbol? Right, that means proportional to. It's kind of like equals, like an equal sign, except that it's not the full equation. It's saying, well, there's probably more to this equation. I haven't said anything about radius or anything about the mass of the swinging canister. Right? But just if I isolate these two variables, I think there's this relationship going on. If that's true, can we do a little algebra? Can you square both sides and say v squared would be proportional to the force? Isn't this line the exact same thing? Right? Just square both sides. Okay. And here's what's cool about this: v squared versus f. Suppose I make a new graph. Okay. Now you guys just made a graph v versus f, and it looks like a square root type relationship. That's where this top expression came from. But what if I manipulate the whole vertical axis and I call this v squared and meters squared per second squared, and I leave the horizontal axis as force and millinewtons? Right now, if our hunch is correct that the original relationship between v and f was a square root relationship, then what does v squared versus f look like? You guys think all these points are going to pretty well line up in a straight line? Pretty much like that. You guys think? Okay. And then if you wanted to, you could get the slope of that line and like pin down more exactly what a formula would be, like an equation for that particular data. So let's switch back over here. All right. Sorry guys, if you're watching that video at home, forgot to switch the screen. So there you go. Real fast. If you're watching a video at home, they're just blown up. Now let's switch back. Switch back over here. Okay. Oh, I meant to refer to you guys here. The lab page. Flip it over. You guys see the back side? So there's 3 graphs on the back. See the very top one says v squared versus weight hanging. All right, that's what we're about to do. So let's switch over. V squared versus weight hanging. Oh, yeah, thank you. All right, there you go. That's that graph. Oh, did you leave it back there? All right. All right, so everybody's making the top graph on the back, right? It's v squared versus weight hanging. Oh, because that could be v squared versus the force. So the vertical axis is v squared. That's the speed squared. And that's in meters squared per second squared. And the horizontal axis is, well, the weight or the force, and that's still in millinewtons, right? I haven't really changed that. All right. Okay. So, guys, labeled and scaled both axes. V squared is in meters squared per second squared. The force is in millinewtons. Right. Okay. Then put the scales axes. So it looks like the v squared goes up to about, or sorry, was that 30? Or is it 50 meters squared per second squared? Looks like the force goes up to about 60 millinewtons, something like that. Okay. All right, and that definitely looks like a direct relationship. I can click on one of these and add trend line. All right, there you go. Oh, look at that. Okay, if I want an equation, here, you can find the slope of that line and then like pin down that relationship, right? Now that is given some particular radius size circle and whatever the mass of the swinging canister would be, right? You could come up with a graph that looks exactly like that. All right, so that is a third of the entire story. Okay, now we have a relationship between the speed of the swinging canister and the weight of the hanging one. Right? Okay, you guys ready for our next relationship? All right, so let me go back to your guys's. Right. How about the other Play-Doh canister? Who was in a group who was changing out the mass of the swinging canister every trial? I know about a third of you guys were. All right. I'm going to grab you guys' data. Thank you. Try this out. So the swinging mass. Oh, before I plug this in, let's do some quick hypothesizing. Guys, if you make the swinging one heavier, how do you have to swing it to keep everything in balance? Faster or slower? Slower, right? Have to slow it down? Or if you like the other way, if you made it lighter, you'd have to spin it faster. Okay, so the masses, we got 50, 20, 10, 30, 40. Right, so there's the masses in grams. Now what's the speeds in meters per second? Oh, look at that. That might be the best graph I've seen all day today. Yeah, so really good job getting your data for that one. All right. Look at that. Really nice inverse relationship going on. That does match our hypothesis, doesn't it? That the greater the mass, the slower you have to spin it. See that inverse relationship? One variable gets big, the other gets small. Yeah.
The M in the weight.
So the mass is in grams, right?
What does VM represent in the graph?
The M represents mass in grams. That's the mass of the swinging canister. Mass in grams. So your vertical axis is still speed in meters per second. Oh, hold on a minute. Yeah. Okay. So it looks like the greatest. I think it's might be off by a factor of 10, but that's all right. The shape is good, right? Looks like it's up to about 60 meters per second. And then the mass would be in grams, right? So you guys are making that's the bottom left graph. You guys, I'm sure, found it by now. The bottom left graph says V versus mass swinging. V versus mass swinging, bottom left graph. So V is in meters per second, and scale it 0 to 70. Mass is in grams, that's the horizontal axis. Scale that 0 to 80 about. Those points about where they go. And there's definitely some kind of inverse relationship going on. Okay. Now I want to use that linearization technique that we just used for the last groups, okay, which is if I could somehow manipulate the axes so that all those points lined up in a direct relationship, okay, which is like the opposite of what's going on here, then I could take the slope of that and pin down more exactly what the relationship is between those two variables. Okay. Now, how would you possibly manipulate the axes to undo a reciprocal? Could you just take the reciprocal of one of those axes? Okay. You could either go 1 over V or 1 over M. Okay. You have to pick one or the other. Okay. Now you could go either way. Either of those might get it closer to a linear relationship. I'm going to do 1 over M just because I know sort of where the slab is going. There's probably lots of ways you could do this, but one way it works out really nice. So we're about to do another graph that's V versus 1 over M. Okay, you guys kind of get that concept? Okay, because this might possibly straighten it out into a direct relationship. And if it doesn't, it'll at least get us a step closer. You guys see the bottom right graph on your lab? You guys see the bottom right graph says V versus 1 over M? Okay, that's the one we're about to do. Okay, you guys ready? Okay, here we go. There's your next graph. Oh, look at that. This might be the best set of data I've ever seen on this one. This is really good data right here. Yeah, so V versus 1 over M. That is exactly what that should look like. I'm for sure going to save this class's data. Save. V versus 1 over M. All right, so everybody's making the bottom right graph on your lab. The vertical axis is still the speed in meters per second. That's what the V stands for today, right? Speed. Okay. And the horizontal axis is not the mass, but the reciprocal of the mass, which would have a unit of 1 over grams, okay? Which is a pretty abstract idea, but still that type of relationship going on between those two. All right, you guys got that graph? So once you have that one, hey, does that look kind of like a square root relationship, just like the last experiment was? I think it does. And if that is true, if it is a square root, well, we already know what to do for the next axis manipulation because it's a process that we just did earlier. Could you guys do V squared versus 1 over M? And that might straighten out into a straight line, right? V squared versus 1 over M. In fact, that is the middle graph on the back. If you flip your page over, look right in the middle, see where it says V squared versus 1 over mass. Okay, so that's the one we're about to do. Okay, you guys ready for that one? V squared versus 1 over mass. Let's see if this lines up in a straight line. Ooh, not exactly, but closer. Okay, let's assume that it is. I mean, it should be pretty close. So I'm gonna say add trend line. Ideally, this would have been so. Let's make believe because the textbook answers that would have been the case. So v squared versus 1 over m. So your vertical axis is v squared. That's in meters squared per second squared. And the horizontal axis is the reciprocal of the mass. So 1 over grams, it's the unit. Okay. All right, and now we have another puzzle piece in place. Okay. So those are both manipulated axes, but the dots are lining up. All right, you guys got that graph? V squared versus 1 over m. Okay, so still working on that one. So this is the middle graph on the back. V squared versus 1 over m. All right. So one way to interpret that, you get like assuming it's a direct relationship, is that if you like tripled the reciprocal of the mass, that you would also be tripling the square of the speed. Kind of a weird way to think about it, but that would say. All right, and we got one experiment to go. All right, so what we're about to do is if you were in a group that was not changing out the masses or the weights of the canisters at all, but you were making different size circles. That's the one we're about to do. Okay. Who was in one of those groups that was doing different size circles? Different size circles. You guys were? Okay. All right. We're gonna grab your data. Gonna find out. Thank you. All right, so the third and last experiment. V versus R. Okay. Oh, let's do some quick hypothesizing. So suppose you're set up a circle, everything's all balanced, it's all good. You say, I want to make a slightly bigger circle. Would you have to spin faster or slower? Yeah, I'm thinking a little faster, right? If you spun it faster, it would open up a bigger circle, right? So I think that this graph is gonna kind of tend up and to the right too, right? But how is it gonna be direct? Is it gonna curve up? Is it gonna curve down? Right? Well, let's get some empirical data and find out. So got these radius values. These are all in meters. Okay. All right, and speeds. That is a really good graph too. That is what that should look like. All right. Thank you. Really good data right there. So you guys know this is the top right graph on the front. Okay. So on the front of your lab page, the top right graph says V versus radius, speed versus radius. Okay. So all else constant. Okay. Yeah, so bigger circles do correspond to faster moving canisters. Okay. And so your vertical axis is speed in meters per second, scale that like 0 to 5. Your horizontal axis is radius in meters, scale that like 0 to 1. Put the dots about where they go. Now we got to figure out what type relationship is that? Is that a direct relationship? Like, Like, is that a straight line? I don't think so. It looks kind of curvy, doesn't it? Okay. How do you guys think that looks? Probably kind of like a square root curve, like we saw a couple of times earlier today already. You guys think like a square root type curve? I think so too. I think that's a square root curve too. In fact, if that is a square root relationship, then can we do the exact same manipulation that we did for like a couple times already today? Okay. You guys ready for next graph? Almost. All right. So we're about to do the last graph. If you flip your lab page over on the back, see where it says v squared versus radius. The last one, v squared versus radius. Okay. So that's what we're about to do. Okay. So we're going to manipulate the entire vertical axis and square it. Okay. And let's see how this turns out. Moment of truth. Bam! Oh, look at that. That is a direct relationship. A trend line. There we go. Yeah. I think I'm gonna probably upload this video to Google Classroom. These are some of the best looking graphs all day today. That's a really good one there. Look at that. That's exactly how that should turn out. For sure, save this. Save. Like that. So see if you like triple the radius of the circle, you'd be tripling not the speed, but the square of the speed. Right. But the speed would go up by a factor of about 1.73, right? Because v squared is proportional to r. All right, so everybody's making the very last graph. It's the bottom graph on the back, v squared versus r. So your vertical axis is the speed squared, and that's in meters squared per second squared. The horizontal axis is the radius, that's in meters. All right, you guys got that one? Good. All right, you guys ready to flip the screen? All right, so we need to crunch all this data. What are we going to do with this? All right, so you guys just did these three. We got v squared versus weight is a direct relationship. V squared versus the reciprocal of the mass is a direct relationship. And v squared versus r, that's one that you guys just saw, is also a direct relationship. So let me write all those on paper. So here, it's these three guys right here, right? You guys just figured out that the speed squared is directly proportional to the hanging weight. The speed squared is directly proportional to the reciprocal of the mass. And the speed squared is also directly proportional to the radius of the circle, right? So the three questions were these three relationships. You guys each did one of these, and here's each individual answer. Okay. Now, the fact that they're all related to v squared, just the way this lab comes together, okay, is really nice. Because if each of these relationships is true individually, can we push them all together into one giant formula? Okay. How about this? V squared is proportional to, let's make one giant formula here, one giant expression. I got a fraction bar set up. Okay. What goes in the numerator? Force and radius. What goes in the denominator? Mass. Okay, you guys see that? Okay. Okay. That right there is the answer to this box. So it says how those four variables related. And I started it for you guys. I said v squared is proportional to that's that much. That's much is type. V squared is proportional to. And then there's the answer. Can you guys just write that? Copy paste it right there. Guys do that? Right, you can write that in that box, right? But there's still another question. It says, therefore solve for F. That's like solve for this force. Right? Because what we're about to do here is come up with an expression that represents centripetal force. Okay? Because remember, this weight is providing this tension, which is acting as a centripetal force holding this canister in a circle. Okay. Now this proportional symbol, treat this sort of like an equal sign. It turns out, by the way, it could be exactly equal to, but that's fine. Can you apply some algebra rules and solve for F?
Is it v squared times r squared?
Exactly. Yeah. F equals mv squared divided by r. Right. Oh, I meant to say proportional too, but actually it turns out, weirdly enough, I am allowed to say equal to exactly. Because it turns out that if you take the slopes of each of these lines, you take the slope, right? Rise over around, and you multiply those three slopes together, not only do the units cancel out so that it's unitless, but also all the numbers multiply to be 1 exactly. So it's 1 times all this stuff, which means you can take this proportional and just turn it into an equals. And that is the answer to the second box. And I'm going to throw a little subscript on this force and call it centripetal force. Okay, centripetal force. Centripetal force. This is like a center seeking force. Okay. Equals center seeking force. Okay. This is the force of like going around a curve. Right? You guys remember Newton's first law of motion says if anything is in motion, it only ever wants to move in straight lines, right? A constant velocity. So if anything's ever going around a curve, there must be some force that's causing that. And here's how you can quantify it. If you know the mass that's going around a curve, the radius of curvature of that curve, and how fast it's going, you just pop it into this expression, boom, you got the force that must be causing that motion. Right? You guys got that? So now you guys know that like the force of turning. Who's got a question? A question. Okay. Right, so hang tight for a few minutes because we're going to do 2 more things with this. 2 more things.
So, quickly though, how does tension work again?
Tension.
It's stuck on this line.
Okay. So guys, is tension a type of force you can measure in newtons? Yeah, right. If this bottom canister, guys, look up here, keep focus. Okay. If this bottom canister is in static equilibrium, right? It's not moving up or down, it's just hanging out there. Then is the tension up equal to the weight down? Yeah, it's the same force. And hey, is the tension of the string going to be the same tension all around? Yeah, it's the same tension. So this tension is equal to, well, it's the same magnitude as this weight, okay? Which is providing the force that's causing us to go into a circle, the centripetal force. Okay. All right. So let's try another thing. Suppose I have this lab mass, put it on this turntable, give this turntable a spin. Take a look at that. Right? Is that right? Now you guys know if I like turned off friction, this would just like fly off in a straight line. Its first law of motion. But I was gonna ask you guys, but I sort of gave away the answer. That is the force that's holding this on the turntable, right? Friction. There's like a frictional force. If it weren't for friction, this wouldn't be able to stay on the turntable. Hey, I wonder if we can calculate what is the force of friction. Let's try this out. We're gonna get to apply this here formula. Okay. So what I have to know? I need to know the mass, the radius of curvature, and also the speed. Right. Well, the mass is pretty easy because it's stamped on here. It says 500 grams. But I'll tell you what, whenever I'm applying formulas, I always want to write things in terms of base SI units. So the mass, 500 grams. I don't want to say grams. Guys, how many kilograms is that? 500 grams. How many kilograms? 0.5. 0.5. Okay. So we got 0.5 kilograms right here. Okay. Oh, I need radius of curvature. Let me grab that. Here. Let's go right here. Pull up a ruler. Okay. Here's about the center of this thing. Okay. I'm gonna say the center's like right here. Let's call it 7 centimeters. Is that okay? 7 centimeters. Right. Now, when you're multiplying numbers in physics and you're coming up with these grand equations, do you want to usually plug centimeters into an expression? Or do you want what? Not centimeters, but meters, right? So 7 centimeters. How many meters is that? Is that 0.07 meters, right? Is that true? Right. Now, oh, what about the speed? That might be kind of tricky to get, right? But you know what? We can get speed the same way that you guys got it yesterday. we can get it through time period. So let me get the time period. One revolution. Okay. So, oh yeah. I'm just gonna make something up. Let's suppose this takes like maybe like 1.2 seconds. I'm just gonna make something up. Okay. 1.2 seconds, just for example. Okay. Hey, now there's enough information lying around that we could calculate speed and therefore the centripetal force provided by friction, like force due to friction. Just hold that in place. Okay. So speed, guys, is speed the same thing as distance over time? So distance over time. Okay. And distance is not like the circumference of the circle for one round trip. So circumference divided by time period. Okay. And is that like 2 pi r divided by time period? I mean, you guys did that yesterday anyway. Okay. So what is 2 pi times r divided by time period? I'm getting 0.37 meters per second, right? So if I pointed a radar gun at that lab mass, spin it around, it'd be going like that fast instantaneously. Okay. All right. Now, let's figure this out. So now I know I call this centripetal force, okay. But in this case, it's provided by friction. So I'll say the frictional force is equal to, see, mv squared over r, right? So m, that's my 0.50 kilograms. V squared, so that's 0.37 meters per second being squared, divided by radius of curvature, okay, which was 0.07 meters. Right. Now, because all these units are in base SI units, kilograms, meters, seconds, right? Notice I don't have grams, I don't have centimeters, nothing like that. Okay. That means that force is naturally going to come out to what unit? What's it? How have you guys been measuring force all along? Newtons. Yeah. 1 Newton is 1 kilogram meter per second squared, isn't it? Okay. So let's see how many newtons this is. 0.5 kilograms. That's 0.37 meters per second. Square the speed. Divided by 0.07 meter radius of curvature. I'm getting the frictional force is 0.978 newtons. Maybe that's too much precision, but it's a tiny bit less than a newton. It's probably pretty close to a newton, right? Okay. Okay, guys got that? Let's take this another way. Let's make believe that as I was spinning this around, what if it was just about to break friction? Like if I spun it any faster, suppose I want to go around in 1.1 seconds. Like, ooh, if I spin a little bit faster, I can shorten this time period. But then it all fails because it breaks friction and like slides off. Right. So suppose this was like maxing out what it could possibly do. Right, you guys get that concept? Okay. Do you think we could calculate the coefficient of static friction? Okay, let's try that out. So I wonder what the coefficient of static friction would have been. Okay. So here's the turntable. Here's like the center of the turntable. Here's the lab weight. Right. It's like on this curved path, right? With this radial size of 7 centimeters. So 0.07 meters. That's lab weight right here. Let's make a free body diagram for that situation where it's on a rotating platform, just going around. Okay. Guys, what's 1 force on this lab weight? What's 1 force? Yeah, true. Yeah, thank you. Here, let's do this this way. This has a weight, mg, of how many newtons? Right, how many newtons weight is this guy? 5, right? 5 newtons. Because 500 grams is 0.5 kilograms. 0.5 times 10 meters per second squared. Yeah, we're looking at 5 newtons. 5 newtons weight. And if it was on a horizontal surface, then what was the normal force? Also 5 newtons, right? Also 5 newtons. Okay. And you guys said there's a frictional force. Now, guys, friction. Guys, which way does friction point as this thing is going around, being pulled around in a circle? Should I do friction to the right or friction to the left? Because imagine here's this plate spinning, right? You guys imagine 3 dimensions. Right? If I just cut off friction, does it want to slide tangent to its motion, which is going to be off this way? according to Newton's first law of motion, just like back into the page, right? Right, right. But it doesn't follow that path. It actually stays on the curved track. Let's see the real version of this, right? See, if I turn off friction like right here, it would just like slide off tangent, choose path of straight line forever, right? But there's something that's pulling it inwards. You know, it's stopping it from going this way. And it's like pulling it inwards, right? Remember just a few months ago, I wrote that centripetal force was a center-seeking force. Here it is, right here. Center-seeking force, right? Centripetal force is always a center-seeking force. If something's going around a curved path, then the centripetal force is the force that's pulling it in towards the center of the circle. It always points to the center of the circle. I'm going to label it force due to friction because it is a frictional force that's acting as the centripetal force, right? Oh, and we have a number for that too. We calculated it. Remember, we got almost 1 Newton. You guys remember that? So 0.978 newtons, and that's really too much precision, but you guys get the idea, right? It's about a Newton, right? So knowing all that, let's put that all together and get coefficient of static friction between these two surfaces. Okay. Again, assuming that it was just about to break friction, like that's maxing out the friction. Okay. Do you guys remember which two forces can give you the coefficient of static friction? It's what divided by what? Well, one of them has to be the friction force, right? And is the other one the normal force? So is that about 1 Newton compared to about 5 Newtons? Okay. Looks like about 1/5, right? So I'm getting a coefficient of static friction of 0.196. Okay. And then Newton per Newton cancels out. Okay. There. Maybe I should really round that up to about 0.2. There you go. That right there could be a reasonable estimate of the coefficient of static friction between those two surfaces. Okay. Right, guys, right there. All right, we're gonna do one more problem today. One more problem. Okay. I got something special for you guys. I'm gonna pull something out of a college textbook that I give to my AP kids. Yeah, you guys are gonna do some college physics. What we got here? A puck of mass 0.25 kilograms, which is half the mass of this guy, is tied to a string allowed to revolve in a circle of radius 1 meter on a frictionless horizontal table. So we have an air hockey table, right? You guys see air hockey? The other end of the string passes through a hole in the center of the table. Oh, hole in the center. And mass 2, 1 kilogram, which is like this guy right here, is tied to it. The suspended mass remains in equilibrium, right? And the top one spins in a circle of constant radius. Hey, does this look almost exactly like your lab yesterday? It sure does, doesn't it? Right? We got the same 4 variables. Well, almost, right? All right, so my AP students are getting these 3 questions. First question, what is the tension in the string? Who can tell me what the tension in that string is? Give you guys a hint. Look at the mass of M2, which has one kilogram of mass. How much does that weigh in newtons? 1 kilogram weighs 10 newtons, right? 10 newtons. So this one weighs 10 newtons and it's in equilibrium. Doesn't that mean the tension up must also be 10 newtons? That's that answer, isn't it? Guess that? Okay. Second question. What is the horizontal force acting on the puck? Oh, what's the answer to that? Is it still 10 newtons? Yeah, because it's all tied together in one string. That string has a tension of 10 newtons. Yeah. Question C. What is the speed of the puck? Notice they give you just enough information you can find out. You know, this is a 10 Newton weight. They told you the radius of curvature was 1 meter. And the mass of this top puck is a quarter of a kilogram. All right, let's figure this out and then we'll call it a day. We can use our new formula. Centripetal force is mv squared over r. Now, in this case, the centripetal force is provided by the tension, right? Okay, which is 10 newtons. So we got 10 newtons. The mass that's on that curved path is a quarter of a kilogram. Moving how fast? Well, we don't know. We're going to solve for that. 1 meter.
Students, please pardon the introduction. We just want to give a reminder about tomorrow's homecoming day of any for that cat. So we report not having received many funds from students providing for their siblings and also live stuff tomorrow. We want them to know that other children and live pets are not permitted.
That ruins my water. I was gonna put it back. I don't. Cody, that was still like this. I leave one.
All right, so turn your lab into the gray tray, and that is a day.